All right, guys, today we are working on our guided notes for worksheets 5/6, and really the main focus of today is symmetry. It is something symmetrical, and we're going to talk about the three different types of symmetry. So I'm actually going to start us over here. What types of symmetry are there? The three that exist and that we're going to focus on today are line symmetry, rotational symmetry, and point symmetry. Those are our three kinds that we're going to work on today. And then what does it mean to carry a shape onto itself? That's another way of saying that a shape has symmetry. So those are interchangeable. We can say a shape has symmetry, and usually at that point we're more specific. Does it have line symmetry or rotational symmetry, for example? We could also say that a shape can carry onto itself. So line symmetry or reflectional symmetry. That means we can map the figure onto itself by using a reflection line. We can map the figure onto itself by using a reflection line. So this will make more sense when we do some examples, which we're going to do right now. On number 1, they've already drawn a line straight down. So really what that means is, in more simple terms, is I could take that A, I could fold it in half right onto itself, and everything would match up. So we're trying to figure out, at this point, how many lines of symmetry these figures have. So A only has one line of symmetry. There's no other place where I could fold this and have my figure match up perfectly. You can also think of it as if I placed a mirror right down the middle here, it would still look the same in its reflection. All right. So how many lines of symmetry does Z have? If I go straight down the center, that wouldn't match up. If I went straight across, that wouldn't match up. I don't think that there are any, so I'm going to write 0. How many lines of symmetry for our butterfly? So again, they've already kind of sketched one here. I think that would work. But straight across here, I don't think these top wings would match up to the bottom wings. So I'm going to say just the 1. And then for our triangle, I think if I tried to do it here, this side is still larger than this side. And then same, if I did that through any of the points, I don't think they would match up perfectly. So I'm going to say 0 here as well. I'm going to erase this line because I don't want to confuse anyone. Number 5, how many lines of symmetry? So again, they sketched them here for us, which is nice. That's not usually how it works where they're already on there, but it looks like we have 1, 2, 3, 4, 5, 6 total lines of symmetry. You don't want to double count. So I started up here and then went around, but if I counted this, I've already counted this line. So you just don't want to count lines twice. For this square, it looks like we have 4 lines of symmetry. Our parallelogram. So parallelograms are sometimes tricky because they look like they might match up, but really this corner ends up being a little off and this corner ends up being a little off if you were to actually fold them. So parallelograms are another shape that have 0 lines of symmetry, but that one's kind of tricky because unless you physically have it to manipulate, it's hard to see that. And then this kind of funky shape here. If I went straight across, I don't think these 2 points would line up. It would kind of look like that. They wouldn't line up perfectly. I'm going to go ahead and say 0 on this one as well. How many lines of symmetry for our arrow? Well, I think we could definitely fold it in half this way. I don't see any others, so I'm going to say just 1. These 2 arcs, I think we could do this again. We couldn't do in half because if I folded it over, I would get one going the opposite direction. So I think that one is also just 1 line of symmetry. Here, I think I could fold it in half and that would match up. And I could fold it in half again. So I'm going to say 2 lines of symmetry. For our B, I think we could do in half, but that's the only one I see. So I'm going to say 1. Our rectangle, we could do in half vertically and horizontally, I believe, for 2. For our triangle here, and this is an equilateral triangle, they're saying all 3 angles are the same, which means all the side lengths are the same too. So straight down looks like it'd be fine, but I should be able to do that through each one of these corners. So that's going to be 3 lines of symmetry. For our heart here, I want to say it's just down the middle. So that'd be 1. And this one looks similar to our equilateral triangle, but I want to say that it would not match up because like this piece would be extending out like that. And I think that would happen on all of them. So I'm going to say 0. So the intricate details don't match up on this one. All right, next page, shade. So it has exactly 1 line of symmetry. So I'm going to assume my line of symmetry is diagonal, and then straight across would be right there. So the main reason, or you could have done the other way and shaded up here, but we could not have done straight down and straight across, because even if we do just straight down, if I flip this over, that's going to shade here. But that's actually 2 lines of symmetry. So the only way to get exactly 1 for this figure was to do it diagonal. So you can already see this one has 2 lines of symmetry. You could have also done 2 diagonals. That would have worked also. Shade, so it has 4 lines of symmetry. So in a square, 4 lines are these 4. So diagonal and then straight across and down. So it looks like it already was horizontal. And then flipping it vertically would look like this. Over this diagonal would look like that. And over this diagonal would look like so. So those 3 would be the ones shaded in. Also, I guess on number 1, if you just left it the way it was, it had 1 line of symmetry horizontally. So here, again, 4 lines of symmetry. So across my horizontal line, oh, not there, would be here. Across my vertical line would be here. Across this diagonal is already just these original shapes, and across this diagonal will give me this box as well. Okay, here it says, what are the characteristics of a polygon that produces the maximum amount of symmetry for its number of sides? So a regular polygon, which means it has it's like a square. So all the same angles and side lengths. That's what regular means. So like in an equilateral triangle, all the angles are the same, all the sides are the same. A square, so they're all congruent. They all measure up. No one side is longer than the other. No angle is bigger than the other. Then it has as many lines of symmetry as sides. So that's why a square has 4, an equilateral triangle has 3. But a rectangle only has 2 because it has different length sides. All right, so now let's take a look at rotational symmetry. So this one says a geometric figure has rotational symmetry if the figure is the image of itself under rotation about a point through any angle whose measure is between 0 and 360 degrees. 0 and 360 are excluded because that would be taking it and just putting it right back on top of itself. That's its starting position. So the angle of rotation is when a shape has rotational symmetry, we sometimes want to know what the angle is. So how many degrees did you have to rotate it to get it back onto itself? To determine this, we determine the smallest angle through which the figure can be rotated to coincide with itself. So there could be, like if you had to rotate it 90 degrees, but then again it happened at 180 and again it happened at 270, we would just do the smallest one at 90 degrees. This number will always be a factor of 360. So like if we take my example of 90 degrees, 180, 270, that does get us back to 360, and they should all go into 360 evenly. And then order of rotation symmetry, the number of positions in which the object looks exactly the same is called the order. So again, if we go back to my 90-degree example, I could turn it a total of 4 times to get back to its starting point. So its order would be 4. When determining order, the last rotation returns object to its original position. Order 1 implies there is no rotational symmetry because you would have to do a complete 360 for it to match back up. All right, so on 21 here, I think if you rotated this, it would take I think it would match up each time you hit another one of these circle dots. So here, if I rotated to here, it would match up, then here, and then back. So if I take 360 divided by 3, because I think it has an order of 3, then my angle of rotation is 120 degrees. For our S, I think it would match up if I rotated about halfway around. So it has an order of 2, and then 360 divided by 2 is 180. This one's going to be very similar to 21 here, where I think every time I hit the corner for a arrow, it's going to line up. So it's an order of 3 or 120 degrees. And then I think for our parallelogram, when we got around to this other corner, it would match up. So this has an order of 2 and 180 degree is the angle. Again, we got a lot of these 3 ones, just like 21 and 23. I think this will line up each time you hit another one of these, I don't know what you want to call them, legs. So that would be an order of 3 or 120 degrees. Same here. I think this is going to match up each time you hit an arrow. For our star, I think it's going to line up each time we hit one of these points. So stars are 5 points, and then 360 divided by 5, I believe, is 72 degrees. And then our Z here, I think, will match up when you get around to the bottom. So this has an order of 2 or 180 degrees. All right, third page, last page. Number 29, this kind of looks like a 4-leaf clover. This is going to match each time you hit a new leaf. So it's an order of 4, which is 90 degrees, 360 divided by 4. This one I don't think will match up again until you get all the way around. So its angle is 360 and has an order of 1. Our orange here, let's count how many segments we have. We have 1, 2, 3, 4, 5, 6, 7, 8, and I think it's going to match up at each segment. So this would be an order of 8, which makes it 45 degrees. And then here, I think this would match up halfway around if you turned it 180 degrees. So an order of 2. All right, 33, shade so it has an angle of 180 degrees, an order of 2. So if I rotate this 180, I would end up here. Angle of 90 or an order of 4. So there's my first 90. If I keep going, 90 more degrees, 90 more degrees, that's what we would get. 180, so halfway around should get me here, and this one would still be on top of itself. 90 would give me, that's my first 90, my second 90, my third 90, and then back to the beginning. And this one would be the same in all 4 of those contexts. All right, and then the last type of symmetry we're going to talk about is point symmetry. So point symmetry exists when a figure is built around a point such that every point in the figure has a matching point that is the same distance from the central point, but in the opposite direction. A simple test to determine whether a figure has point symmetry is to turn it upside down and see if it looks the same. So if you rotate it 180 degrees, does it look the same? A figure that has point symmetry is unchanged by 180 degree rotation. All shapes that have point symmetry have rotational symmetry with an even order. So for example, this S has an order of 2. And point symmetry is saying that if I take the dead middle of this S, if I put a point here, I have one in the same distance over here. And there's infinite numbers of points on this S. Like if I wanted to even add another one here, same distance on the other side is going to be right here. Okay, so these are not all the possible ones. There's an infinite amount. But we're just saying if I put a point, they're going to be the same distance on either side. This is a hexagon, so it has an order of 6. But that's even, and any point you put is going to be the same distance on either side from the center. Again, here it looks like if I turn this upside down, it would look the same. This one I think would just have an order of 2, but that still works. And then here, again, we have an order of 2 if I flip it 180 degrees, and then there are infinite points you could use. I could even add one here, but we're just saying that has a special relationship where these are the same distance from the center. You will notice that the point of rotation is the midpoint between every point and its image. So the very center is a midpoint. All right, so that's it for today's notes. You are working on worksheet 5/6 in your packet, which are pages 27 and 28.